to get ready to record our lesson from the Infinite Geometric Series. And you're just going to have to live through a few bells and maybe an announcement that comes in partway. I'll try to get this recorded so that those of you who missed the class have something to take a look at. So we're looking at the Infinite Geometric Series from section 1.5. And in this lesson, what we attempted to do was to help you understand the idea of the infinite geometric series and its formula. And then, of course, once you had the formula in hand, to try a few questions with it before you attempted your homework. For vocabulary, make sure that you're looking for two things, the convergent series and the divergent series. Now, we started the lesson with this interesting situation that was posed by a Greek philosopher, Zeno of Elea. We call these the paradoxes of Zeno. The one that we took a look at was called his paradox of motion, that said, a person standing in a room cannot walk to the opposite wall. It kind of makes your head tilt and you think, whoa, what on earth is he thinking here? Well, let's take a look at it. What he was posing was that if you are at one wall and must reach the other one, first of all, you must go halfway. And once you're halfway, then you must go half of the remaining distance, which would mean that you would travel 1/4. Once you're there, you must travel 1/2 of the remaining distance, which would be 1/8. And then again, half of the remaining distance at 1/16, half of the remaining distance at 1/32, half of the remaining distance at 1/64, half at 1/128, and so on. So in theory, you would always be that little tiny distance away from the other wall. Now, clearly, in our understanding of physical space and time, this is not really something that we grapple with, but the idea of it is where we started. We also in class took an example of a pattern to help us understand the idea of an infinite series. What we had was a square piece of paper, and we took the square piece of paper and divided it by folding it lengthwise, and we colored one side of it. And then the remaining part, which would have been blank at the time, we folded it once again and we colored half of it. And then the top part, we folded it once again and we colored again. And we kept on doing this pattern, and gradually, little by little, we came to this pattern where we were coloring and we always had a tiny little space that was uncolored. And then we took these and wrote them down as numbers. We, first of all, had shaded half of it, and then 1/4, and then 1/8. And we wrote this down as a pattern and said that basically when we talked about the shaded portion of our square, it's as if we were taking this geometric series and finding what it actually added up to. And so we used a geometric pattern to kind of write this down. Our first term was 1/2. The ratio in this case from term to term would be 1/2. So here was our general term. Now, ignoring, if we were to imagine that we were not limited by the limitations of our physical world, the question was, could this sequence continue indefinitely? Yes, of course it could. We might need a magnifying glass to get to the spot where we're dividing this in half and shading it. We might need a microscope and a tiny, tiny little stylus or pen to be able to shade it. But in theory, if we were not limited by physical space, we could keep on going indefinitely. An infinite geometric series. Here comes an announcement.
Titans, we've gone through 3 sessions. We're going to give you a 10-minute recess break, and then we'll be back on the PA to send you back to your next session that you have on your sheet. So hang on to those sheets. Thank you.
Okay, now the interesting part about this was, what if we took this particular pattern and wrote it out so that we could actually put it into our graphing calculators? So in other words, we create the series pattern. We use an X instead of a number on the bottom, because we're just pretending what happens if this number gets bigger and bigger. And we put in the first term. We put in 1 minus 1/2 to the power of X over 1 minus 1/2. What I'm using is my sum formula. Now you'll notice that I've switched places between the ones and the ratios. As long as we do that to the numerator and the denominator, we're keeping a balance within this formula, and so it doesn't hurt anything. And if I were to take a look at this just a little closer, I have 1/2 on top. I've got 1/2 on the bottom. and a half divided by half is gone. So really all I have is the following. And what we did was we took this and put it into our graphing calculators. And we graphed it in 1 minus 1/2 to the power of x. And rather than graphing this, actually checking to see on the graph, what we did instead was we looked at the table of values. And these are what we saw. Now, interestingly enough, as our number, as the x got larger and larger, and you could go further than this, of course, our numbers started to get really, really close to 1. It became a 1. And so remember, this series represents what we were doing when we were shading that square. Well, we were shading it gradually, and we could tell that gradually we were shading the 1 square. But this also shows us numerically that we were getting close to, all those numbers added together were really, really close to a 1. Well, then we tried another series. So we tried this one, which started with a 4, but still had a ratio of 1/2. And we plugged that one in. And then we took this one and we plugged it into our graphing calculators. And when we did, we discovered this time that the numbers got really, really close to an 8. So we say that as the number of terms increased in this particular series, the sequence approached a fixed value of 8. The sum of the series was 8. We say that this series is a convergent series, meaning that the series is converging onto the number 8. On the other hand, we tried a series that looked like this one, where we started with 4, but this time our ratio was 2, and all that was happening was each number was getting larger than the one before it. Well, when we tried to play around with this one and put it into the graphing calculator, what we found was that the series was not converging on anything. It was just getting bigger and bigger and bigger and bigger. And so we said that this series is a divergent series. It does not converge onto a particular number. It diverges off into infinity, really, is what's happening. So using these ideas, we realized that if we had an infinite series where the ratio was a fraction, it seemed as though the series would converge onto a number. If the ratio was larger than a 1, then it went to infinity. And that gave us a formula that we could use. And here it is. This is where it starts that you need to remember. The sum of an infinite geometric series where the ratio is smaller than 1 or bigger than -1. So it will actually work for negative fractions as well. We can use the following formula to calculate what the sum actually is. The sum of an infinite number of terms is the first term divided by 1 minus r. So the previous work that we've done was really to try and help you understand what an infinite geometric series looks like, what it behaves like, to begin to see convergent series and divergent series, and then to give you the following formula. So we only have a couple of questions that we tried. The first one, you're being asked to decide whether the series is convergent or divergent. So let's take a look at these. The first one. First term is 1. The ratio is -1/3. This one falls under the definition of what we call a convergent series. So we use our formula. The first term is a 1. We write 1 minus -1/3. 1 minus -1/3 is 4/3. And when I flip that, this one converges on 3/4. If I look at the second one, the first term is a 2, and the ratio is -2. This is not a convergent series. It is divergent, so therefore there is no sum. The last one we did was another pattern. It said, assume that the shaded square down below represents 1/4 of the area of the larger squares. So this is 1/4 of the big one. Write the series of terms that represents this scenario. And so we had 1/4, and then the next one, when we colored this one, it's dividing everybody into 4. That would be 1/16, and so on. Now let me go back here for a second. And so the next one was 1/64. So my first term is 1/4, and my ratio is 1/4. Then if I take a look at that and say, how much is the total area of these shaded squares? So I use my formula. The first term is 1/4. The ratio is 1 minus 1 over 4. Go ahead and flip these guys. I get an answer of 1/3. And interestingly enough, you can kind of imagine that these shaded parts is about 1/3 of the area of my square. Okay, there you have it. A few questions that give you an example of what to do. Very, very important that you do your homework this time around and make sure you bring your questions to class. Okay, good luck, everybody.